In the previous section, you learned that the limit of f of x as x approaches c does not depend on the actual value of f at x equals c. Taking a look at the left graph, if I want to find the limit as x approaches 2 of f of x, notice that as we get closer and closer to 2 from either direction, in the y-axis, we're going to get closer and closer to 2 from both directions as well. So the limit as x approaches 2 of f of x equals 2. However, if I try to evaluate the function at 2, I'm going to get 0. Because the limit and the value of the function at 2 are two different values, we say that the function is not a well-behaved function. On the right, however, if I want to find the limit as x approaches 2 of f of x, then as I get closer and closer to 2 from either direction, in the y-axis, I'm going to get closer and closer to 4. So the limit as x approaches 2 of f of x is equal to 4. If I evaluate the function at 2, replace the x with a 2, so 2 squared, that's also going to give me 4. If it turns out that the limit and the function at the particular value that we're interested in are the same thing, then we say the graph is a well-behaved graph. And if it's a well-behaved graph or a well-behaved function, then we can use direct substitution to evaluate the limit. Before we see what direct substitution is, let's take a look at some basic limits. So I want to take the limit as x approaches 2 of the constant function f of x equals 3. What's that? Well, according to that rule up there, this is simply going to be 3. So the limit as x approaches 2 of 3 is 3. If I want to find the limit as x approaches negative 4 of f of x equals x, I'm going to replace the x with the value that I'm approaching. So the limit as x approaches negative 4 of x equals negative 4. And then lastly, if I want to find the limit as x approaches 2 of the function f of x equals x squared, then I'm going to replace the x with the 2. I'm going to square it. 2 squared equals 4. And in general, if you're adding or subtracting, multiplying, or dividing functions and you want to find the limit of that composition, we're going to follow the rules on the right. So now let's take a look at the following limit. What's the limit as x approaches 2 of 4x squared plus 3? My solution is going to be, notice that 4x squared plus 3 is, or it can be considered the sum of two functions. 4x squared is one function, and then the constant function 3 is another. So I can rewrite the limit as the limit of 4x squared plus 3 equals the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. Because there's a constant in front of the x squared, I can bring it to the front of the limit statement. So the limit as x approaches 2 of x squared, and then the limit as x approaches 2 of 3 is simply 3. Using direct substitution, I can plug in 2 for x. 4 times 4 is 16. 16 plus 3 is going to give me 19. Notice that the limit of a polynomial function is the same thing as the polynomial evaluated at x equals 2. So direct substitution is going to be valid for all polynomials and rational functions that don't give you a 0 in the denominator. Now we're going to look at something similar. What is the limit of a rational function? So I want to find the limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. So my solution is going to look like this. I'm going to use the quotient rule. The limit as x approaches 1 of x squared plus x plus 2 over x plus 1. I have a polynomial in the numerator and a polynomial in the denominator. So I can go ahead and do direct substitution Anywhere I see an x, I'm going to put in the number 1. In the numerator, I get 1 plus 1 plus 2, which is 4. And then when I divide 4 by 2, I get 2. So the limit as x approaches 1 of the rational function is going to equal 2. The last way that we can combine functions is through composition. So what would the limit of a composition function look like? What's key about composition functions is that you have to make sure that the inner function, in this case g of x, you have to make sure that that function is a well-behaved function, such as a polynomial. If that's the case, then we can find the limit of any composition by taking the limit statement, bringing it inside f of x, evaluating the limit as x approaches c of g of x, which should give you a number. Let's call that number L. Then once you have that number L, you can evaluate f at that value. So let's take a look at more concrete functions. So let's call f of x the square root of x, and let's call g of x x squared plus 4. And I want to find the limit as x approaches 0 of the composition f of g of x. So in my solution, I'm always going to start by first rewriting the problem, the limit as x approaches 0 of f of g of x. So the outside function is going to be the square root of x. So I'm going to keep the square root part, and I'm going to evaluate it at g of x, which is x squared plus 4. Notice that x squared plus 4 is a polynomial, so it is going to be a well-behaved function. You can use direct substitution when evaluating that limit. So let's bring the limit inside of the square root. And like I said, it's a polynomial, so we can replace x with 0. So the square root of 0 plus 4, which is simply the square root of 4, which we're going to take the positive value 2. Taking a look at another example, let's call f of x the cube root of x. Let's call g of x 2x squared minus 10. And we're interested in finding the limit as x approaches negative 3 of the composition f of g of x. So here's how the solution is going to look. The limit as x approaches negative 3. The outside function is the cube root function, and then you're going to evaluate the cube root at g of x. The inner function, g of x, is a well-behaved function, so we can bring the limit statement inside of the cube root and evaluate the limit as x approaches negative 3 of g of x, which, because it's a polynomial, we're going to use direct substitution. Anywhere that I see an x, I'm going to put in the number negative 3. I'm going to get 18 minus 10 underneath the cube root, which ends up being the cube root of 8, which is 2. To conclude, we can use direct substitution to solve limit problems so long as those functions that we're dealing with are well-behaved functions. An example of well-behaved functions would be polynomial functions, rational functions, so long as you don't have a 0 in the denominator, because a rational function is just two polynomials dividing each other. But we can also use direct substitution for things that are not polynomials, such as trig functions. We can also do it for exponential functions. They are well-behaved. And logarithmic functions are also well-behaved functions where we can use direct substitution. Here are some quick example of the last three. So let's say we want to find the limit as x approaches 0 of tangent of x. Tangent is a well-behaved function, so we can use direct substitution. Anywhere I see an x, I'm going to put in 0. Tangent of 0 is 0. The limit as x approaches -1 of x times e to the x. So e to the x is an exponential. Anywhere I see an x, replace it with -1. And then the limit as x approaches e of the natural log of x cubed. Using properties of exponent, we can bring the 3 in the front, evaluate the natural log of e, which is 1. So the value is 3.